Ray optics and optical instruments. Introduction. Nature has endowed the human eye, retina, with the sensitivity to detect electromagnetic waves within a small range of the electromagnetic spectrum. Electromagnetic radiation belonging to this region of the spectrum, wavelength of about 400 nanometers to 750 nanometers, is called light. It is mainly through light and the sense of vision that we know and interpret the world around us. There are two things that we can intuitively mention about light from common experience. First, that light travels with enormous speed, and second, that it travels in a straight line. It took some time for people to realize that the speed of light is finite and measurable. Its presently accepted value in vacuum is c equals 2.9979245 times 10 power 8 meters s power minus 1. For many purposes, it suffices to take c equals 3 times 10 power 8 meters s power minus 1. The speed of light in vacuum is the highest speed attainable in nature. The intuitive notion that light travels in a straight line seems to contradict what we have learnt in Chapter 8, that light is an electromagnetic wave of wavelength belonging to the visible part of the spectrum. How to reconcile the two facts? The answer is that the wavelength of light is very small compared to the size of ordinary objects that we encounter commonly, generally of the order of a few cm or larger. In this situation, as you will learn in Chapter 10, a light wave can be considered to travel from one point to another, along a straight line joining them. The path is called a ray of light, and a bundle of such rays constitutes a beam of light. In this chapter, we consider the phenomena of reflection, refraction and dispersion of light, using the ray picture of light. Using the basic laws of reflection and refraction, we shall study the image formation by plane and spherical reflecting and refracting surfaces. We then go on to describe the construction and working of some important optical instruments, including the human eye. Reflection of light by spherical mirrors. We are familiar with the laws of reflection. The angle of reflection, i.e., the angle between reflected ray and the normal to the reflecting surface or the mirror, equals the angle of incidence, angle between incident ray and the normal. Also that the incident ray, reflected ray and the normal to the reflecting surface at the point of incidence lie in the same plane, figure 9.1. These laws are valid at each point on any reflecting surface whether plane or curved. However, we shall restrict our discussion to the special case of curved surfaces, that is, spherical surfaces. The normal in this case is to be taken as normal to the tangent to surface at the point of incidence. That is, the normal is along the radius, the line joining the center of curvature of the mirror to the point of incidence. We have already studied that the geometric center of a spherical mirror is called its pole, while that of a spherical lens is called its optical center. The line joining the pole and the center of curvature of the spherical mirror is known as the principal axis. In the case of spherical lenses, the principal axis is the line joining the optical center with its principal focus, as you will see later. Sign convention. To derive the relevant formulae for reflection by spherical mirrors and refraction by spherical lenses, we must first adopt a sign convention for measuring distances. In this book, we shall follow the Cartesian sign convention. According to this convention, all distances are measured from the pole of the mirror or the optical center of the lens. The distances measured in the same direction as the incident light are taken as positive, and those measured in the direction opposite to the direction of incident light are taken as negative, figure 9.2. The heights measured upwards with respect to x-axis and normal to the principal axis, x-axis, of the mirror lens are taken as positive, figure 9.2. The heights measured downwards are taken as negative. With a common accepted convention, it turns out that a single formula for spherical mirrors and a single formula for spherical lenses can handle all different cases. Focal length of spherical mirrors. Figure 9.3 shows what happens when a parallel beam of light is incident on a concave mirror, and b, a convex mirror. We assume that the rays are paraxial, that is, they are incident at points close to the pole P of the mirror and make small angles with the principal axis. The reflected rays converge at a point F on the principal axis of a concave mirror, figure 9.3 For a convex mirror, the reflected rays appear to diverge from a point F on its principal axis, figure 9.3 b. The point F is called the principal focus of the mirror. If the parallel paraxial beam of light were incident, making some angle with the principal axis, the reflected rays would converge, or appear to diverge, from a point in a plane through F normal to the principal axis. This is called the focal plane of the mirror, figure 9.3, c. The distance between the focus F and the pole P of the mirror is called the focal length of the mirror, denoted by F. We now show that F equals R2, where R is the radius of curvature of the mirror. The geometry of reflection of an incident ray is shown in figure 9.4. Let C be the center of curvature of the mirror. Consider a ray parallel to the principal axis striking the mirror at M, then CM will be perpendicular to the mirror at M.
The measure of angle MCP equals theta and measure of angle MFP equals 2 theta. So tan theta can be written as MD by CD and tan 2 theta equal to MD by FD. That's the equation 9.1. For small angles of theta, which is true for paraxial rays, tan theta can be approximately written as theta. So tan 2 theta can also be written as 2 theta. Therefore, this equation 9.1 gives MD by FD equals 2 times MD by CD. So FD equal to CD by 2. Now for small angles of theta, the point D is very close to the point P. Therefore, FD equal to F and CD equal to R. So the equation 9.2 then gives us F is equal to R by 2. That's half of the radius of curvature. The mirror equation. If the rays emanating from a point actually meet at another point after reflection and or refraction, the point is called the image of the first point. The image is real if the rays actually converge to the point. It is virtual if the rays do not actually meet but appear to diverge from the point when produced backwards. An image is just a point-to-point correspondence with the object established through reflection and or refraction. In principle, we can take any two rays emanating from a point on an object, trace their paths, and find their point of intersection, and thus obtain the image of the point due to reflection at a spherical mirror. In practice, however, it is convenient to choose any two of the following rays. The ray from the point which is parallel to the principal axis. The reflected ray goes through the focus of the mirror. The ray passing through the center of curvature of the concave mirror or appearing to pass through it for a convex mirror. The reflected ray simply retraces the path. Then, the ray passing through or directed towards the focus of the concave mirror or appearing to pass through or directed towards the focus of the convex mirror. The reflected ray is parallel to the principal axis. The ray incident at any angle at the pole. The reflected ray follows the laws of reflection. The figure 9.5 shows the ray diagram considering three rays. It shows the image A dash B dash, in this case which is real, of an object AB formed by a concave mirror. So it does not mean that only three rays emanate from the point A. An infinite number of rays emanate from any source in all directions. Thus point A dash is the image point of A if every ray originating at point A and falling on the concave mirror after reflection passes through it. We now derive the mirror equation or the relation between the object distance, image distance and the focal length. That's the mirror equation. From the figure 9.5, the two right angle triangles A dash B dash F and MPF are similar. For paraxial rays, MP can be considered to be a straight line perpendicular to CP. Therefore, B dash A dash by PM equal to B dash F by FC, or B dash A dash by BA is equal to B dash F by FC. That is because PM is equal to AB. Since the angle APB is equal to angle A dash B dash, the right angle triangles A dash B dash P and ABP are also similar. Therefore, B dash A dash by BA is equal to B dash P by BP. Comparing the equations 9.4 and 9.5, we will get B dash F by Fp is equal to B dash P minus Fp by Fp. and thus given by B dash P by BP. Equation 9.6 is a relation involving magnitude of distances. We now apply the sign convention. We note that light travels from the object to the mirror MPN. Hence, this is taken as the positive direction. To reach the object AB, image A dash B dash as well as the focus F from the pole P, we have to travel opposite to the direction of incident light. Hence, all the three will have negative signs. Thus, B dash P is equal to minus V, FP equal to minus F, and BP equal to minus U. Using this in equation 9.6, we will get the expression as V by F is equal to 1 plus V by U. Dividing this equation by V, we will get 1 by V plus 1 by U equal to 1 by F. So this relation is called as the mirror equation. The size of the image relative to the size of the object is another important quantity to be considered. We now define the linear magnification as the ratio of the height of the image h dash to the height of the object h. So magnification m is given by h dash by h. Here h and h dash will be taken positive or negative in accordance with the accepted sign convention. In triangle C dash B dash P and ABP, we have B dash A dash by BA equal to B dash P by BP. So with the sign convention, this will become minus H dash by H is equal to minus V by U.
With the sign convention, this becomes minus h dash by h equals minus v by minus u. So that m equals h dash by h equals minus v by u, 9.9. We have derived here the mirror equation, 9.7, and the magnification formula, equation, 9.9, for the case of real, inverted image formed by a concave mirror. With the proper use of sign convention, these are, in fact, valid for all the cases of reflection by a spherical mirror, concave or convex, whether the image formed is real or virtual. Figure 9.6 shows the ray diagrams for virtual image formed by a concave and convex mirror. You should verify that equations 9.7 and 9.9 are valid for these cases as well. Refraction. When a beam of light encounters another transparent medium, a part of light gets reflected back into the first medium while the rest enters the other. A ray of light represents a beam. The direction of propagation of an obliquely incident, 0 degrees less than I less than 90 degrees, ray of light that enters the other medium, changes at the interface of the two media. This phenomenon is called refraction of light. Snell experimentally obtained the following laws of refraction. The incident ray, the refracted ray and the normal to the interface at the point of incidence, all lie in the same plane. The ratio of the sine of the angle of incidence to the sine of angle of refraction is constant. Remember that the angles of incidence, I, and refraction, R, are the angles that the incident and its refracted ray make with the normal, respectively. We have the equation 9.10 where n21 is a constant, called the refractive index of the second medium with respect to the first medium. Equation 9.10 is the well-known Snell's law of refraction. We note that n21 is a characteristic of the pair of media, and also depends on the wavelength of light, but is independent of the angle of incidence. From EQ 9.10, if n21 greater than 1, r less than I, that is the refracted ray bends towards the normal. In such a case medium 2 is said to be optically denser, or denser in short than medium 1. On the other hand, if n21 less than 1, r greater than I, the refracted ray bends away from the normal. This is the case when incident ray in a denser medium refracts into a rarer medium. If n21 is the refractive index of medium 2 with respect to medium 1 and n12 the refractive index of medium 1 with respect to medium 2, then we get the equation 9.11. It also follows that if n32 is the refractive index of medium 3 with respect to medium 2 then n32 equals n31 times n12, where n31 is the refractive index of medium 3 with respect to medium 1. Some elementary results based on the laws of refraction follow immediately. For a rectangular slab, refraction takes place at two interfaces, air glass and glass air. It is easily seen from figure 9.9 that R2 equals I1, that is, the emergent ray is parallel to the incident ray. There is no deviation, but it does suffer lateral displacement, shift with respect to the incident ray. Another familiar observation is that the bottom of a tank filled with water appears to be raised, figure 9.10. For viewing near the normal direction, it can be shown that the apparent depth, h1, is real depth, h2, divided by the refractive index of the medium, water. Total internal reflection. When light travels from an optically denser medium to a rarer medium at the interface, it is partly reflected back into the same medium and partly refracted to the second medium. This reflection is called the internal reflection. When a ray of light enters from a denser medium to a rarer medium, it bends away from the normal, for example, the ray A01b in figure 9.11. The incident ray A01 is partially reflected, O1c, and partially transmitted, O1b, or refracted, the angle of refraction, R, being larger than the angle of incidence, I. As the angle of incidence increases, so does the angle of refraction. Till for the ray A03, the angle of refraction is pi by 2. The refracted ray is bent so much away from the normal that it grazes the surface at the interface between the two media. This is shown by the ray A03d in figure 9.11. If the angle of incidence is increased still further, example, the ray A04, refraction is not possible, and the incident ray is totally reflected. This is called total internal reflection. When light gets reflected by a surface, normally some fraction of it gets transmitted. The reflected ray, therefore, is always less intense than the incident ray, howsoever smooth the reflecting surface may be. In total internal reflection, on the other hand, no transmission of light takes place. The angle of incidence corresponding to an angle of refraction 90 degrees, say angle αn, is called the critical angle, I, for the given pair of media. We see from Snell's law, equation 9.10, that if the relative refractive index of the refracting medium is less than 1, then, since the maximum value of sin r is unity, there is an upper limit to the value of sin I for which the law can be satisfied, that is, I equals IC such that sin IC equals N21, 9.12. For values of I larger than IC, Snell's law of refraction cannot be satisfied, and hence no refraction is possible. The refractive index of denser medium 1 with respect to rarer medium 2 will be N12 equals 1, sin IC. Some typical critical angles are listed in table 9.1. A demonstration for total internal reflection. All optical phenomena can be demonstrated very easily with the use of a laser torch or pointer, which is easily available nowadays. Take a glass beaker with clear water in it. Add a few drops of milk or any other suspension to water and stir so that water becomes a little turbid. Take a laser pointer and shine its beam through the turbid water. You will find that the path of the beam inside the water shines brightly. Shine the beam from below the beaker such that it strikes at the upper water surface at the other end. Do you find that it undergoes partial reflection, which is seen as a spot on the table below, and partial refraction, which comes out in the air and is seen as a spot on the roof? Figure 9.12. Now direct the laser beam from one side of the beaker such that it strikes the upper surface of water more obliquely. Figure 9.12b. Adjust the direction of laser beam until you find the angle for which the refraction above the water surface is totally absent and the beam is totally reflected back to water. This is total internal reflection at its simplest. Pour this water in a long test tube and shine the laser light from top, as shown in figure 9.12c. Adjust the direction of the laser beam such that it is totally internally reflected every time it strikes the walls of the tube. This is similar to what happens in optical fibers. Take care not to look into the laser beam directly and not to point it at anybody's face. Total internal reflection in nature and its technological applications. Prism. Prisms designed to bend light by 90 or by 180 make use of total internal reflection, figure 9.13, and b. Such a prism is also used to invert images without changing their size, figure 9.13, c. In the first two cases, the critical angle IC for the material of the prism must be less than 45. We see from table 9.1 that this is true for both crown glass and dense flint glass. Optical fibers. Nowadays optical fibers are extensively used for transmitting audio and video signals through long distances. Optical fibers too make use of the phenomenon of total internal reflection. Optical fibers are fabricated with high-quality composite glass, quartz fibers. Each fiber consists of a core and cladding. The refractive index of the material of the core is higher than that of the cladding. When a signal in the form of light is directed at one end of the fiber at a suitable angle, it undergoes repeated total internal reflections along the length of the fiber and finally comes out at the other end, figure 9.14. Since light undergoes total internal reflection at each stage, there is no appreciable loss in the intensity of the light signal. Optical fibers are fabricated such that light reflected at one side of inner surface strikes the other at an angle larger than the critical angle. Even if the fiber is bent, light can easily travel along its length. Thus, an optical fiber can be used to act as an optical pipe. A bundle of optical fibers can be put to several uses. Optical fibers are extensively used for transmitting and receiving electrical signals which are converted to light by suitable transducers. Obviously, optical fibers can also be used for transmission of optical signals. For example, these are used as a light pipe to facilitate visual examination of internal organs like esophagus, stomach and intestines. You might have seen a commonly available decorative lamp with fine plastic fibers with their free ends forming a fountain-like structure. The other end of the fibers is fixed over an electric lamp. When the lamp is switched on, the light travels from the bottom of each fiber and appears at the tip of its free end as a dot of light. The fibers in such decorative lamps are optical fibers. The main requirement in fabricating optical fibers is that there should be very little absorption of light as it travels for long distances inside them. This has been achieved by purification and special preparation of materials such as quartz. In silica glass fibers, it is possible to transmit more than 95% of the light over a fiber length of 1 kilometer. Compare with what you expect for a block of ordinary window glass 1 kilometer thick. Refraction at spherical surfaces and by lenses. We have so far considered refraction at a plane interface. We shall now consider refraction at a spherical interface between two transparent media. An infinitesimal part of a spherical surface can be regarded as planar and the same laws of refraction can be applied at every point on the surface. Just as for reflection by a spherical mirror, the normal at the point of incidence is perpendicular to the tangent plane to the spherical surface at that point and, therefore, passes through its center of curvature. We first consider refraction by a single spherical surface and follow it by thin lenses. A thin lens is a transparent optical medium bounded by two surfaces, at least one of which should be spherical. Applying the formula for image formation by a single spherical surface successively at the two surfaces of a lens, we shall obtain the lens maker's formula and then the lens formula. Refraction at a spherical surface. Figure 9.15 shows the geometry of formation of image I of an object O on the principal axis of a spherical surface with center of curvature C, and radius of curvature R. The rays are incident from a medium of refractive index N1, to another of refractive index N2. As before, we take the aperture, or the lateral size, of the surface to be small compared to other distances involved, so that small angle approximation can be made. In particular, nanometer will be taken to be nearly equal to the length of the perpendicular from the point N on the principal axis. We have, for small angles, the following equation.
Tan of the angle NCM equal to Mn by Mc, and tan of the angle NIM equal to Mn by Mi. Now for the triangle NOC, I is the exterior angle. Therefore, I is equal to angle NYM plus meter of angle NCM. So I equal to Mn by OM plus Mn by MC. Similarly, R is equal to tan angle NCM minus angle NIM, that is R equal to M1 by MC minus M1 by MI. Now by Snell's law, we have N1 in sin I equal to N2 sin R. R for small angles, N1 I equal to N2 R. Substituting for I and R from the equations 9.13 and 9.14, we get N1 by OM plus N2 by MI equal to N2 minus N1 by MC. Here, OM, MI and MC represent magnitudes of distances. Applying the Cartesian sign convention, we have OM equal to minus U, MI equal to plus V, and MC equal to plus R. Substituting this in the equation 9.15, we will get the equation as N2 by V minus N1 by U equal to N2 minus N1 by R. This equation 9.16 gives us the relation between the object and the image distance in terms of refractive index of the medium and the radius of curvature of the curved spherical surface. It holds for any curved spherical surface. Refraction by a lens. The figure 9.16 shows the geometry of image formation by a double convex lens. The image formation can be seen in terms of two steps. The first one is the refracting surface forms the image I1 of the object O. That is figure 9.16b. The image I1 acts as a virtual object for the second surface that forms the image at I. That is figure 9.16c. Applying the equation 9.15 to the first interface ABC, we get N1 by OB plus N2 by DI1 equal to N2 minus N1 by DC1. A similar procedure applied to the second interface ABC gives minus N2 by DI1 plus N1 by DI equal to N2 minus N1 by DC2. For a thin lens DI1 equal to DI1, adding the equations 9.17 and 9.18, we get N1 by OB plus N1 by DI equal to N2 minus N1 into 1 by DC1 plus 1 by DC2. Suppose the object is at infinity, that is OB moving to infinity and DI equal to F. The equation 9.19 gives N1 by F equal to N2 minus N1 into 1 by DC1 plus 1 by DC2. The point where image of an object placed at infinity is formed is called the focus F of a lens, and the distance F gives its focal length. A lens has two foci, F and F dash, on either side of it. By the sign convention, we have DC1 equal to plus R1 and DC2 equal to minus R2. So the equation 9.20 can be written as 1 by F equal to N21 minus 1 into 1 by R1 minus 1 by R2. That is by N21 equal to N2 by N1. The equation 9.21 is known as the lens maker's formula. It is useful to design lenses of desired focal length using surfaces of suitable radii of curvature. Note that the formula is true for a concave lens also. In that case, R1 is negative and R2 is positive, and therefore the focal length F is negative.
From equations 9.19 and 9.20, we get the equation 9.22. Again, in the thin lens approximation, B and D are both close to the optical center of the lens. Applying the sign convention, we get the equation 9.23. This equation, 9.23, is the familiar thin lens formula. Though we derived it for a real image formed by a convex lens, the formula is valid for both convex as well as concave lenses and for both real and virtual images. It is worth mentioning that the two foci, f and f', of a double convex or concave lens are equidistant from the optical center. The focus on the side of the original source of light is called the first focal point, whereas the other is called the second focal point. To find the image of an object by a lens, we can, in principle, take any two rays emanating from a point on an object, trace their paths using the laws of refraction and find the point where the refracted rays meet, or appear to meet. In practice, however, it is convenient to choose any two of the following rays. 1. A ray emanating from the object parallel to the principal axis of the lens after refraction passes through the second principal focus f, in a convex lens, or appears to diverge, in a concave lens, from the first principal focus f2. A ray of light, passing through the optical center of the lens, emerges without any deviation after refraction. 3. A ray of light passing through the first principal focus of a convex lens, figure 9.17, emerges parallel to the principal axis after refraction. B. A ray of light incident on a concave lens appearing to meet the principal axis at second focus point emerges parallel to the principal axis after refraction, figure 9.17, b. Figures 9.17, and b illustrate these rules for a convex and a concave lens, respectively. You should practice drawing similar ray diagrams for different positions of the object with respect to the lens, and also verify that the lens formula, equation 9.23, holds good for all cases. Here again it must be remembered that each point on an object gives out infinite number of rays. All these rays will pass through the same image point after refraction of the lens. Magnification, m, produced by a lens is defined, like that for a mirror, as the ratio of the size of the image to that of the object. Proceeding in the same way as for spherical mirrors, it is easily seen that for a lens m equals h by h equals v by u. When we apply the sign convention, we see that, for a rect and virtual image formed by a convex or concave lens, m is positive, while for an inverted and real image, m is negative. Power of a lens. Power of a lens is a measure of the convergence or divergence, which a lens introduces in the light falling on it. Clearly, a lens of shorter focal length bends the incident light more, while converging it in case of a convex lens and diverging it in case of a concave lens. The power P of a lens is defined as the tangent of the angle by which it converges or diverges a beam of light parallel to the principal axis falling at unit distance from the optical center, figure 9.18. Tan delta equals h by f. If h equals 1, tan delta equals 1 by f, or delta equals 1 by f for small value of delta. Thus P equals 1 by f. The SI unit for power of a lens is diopter, d, 1 d equals 1 m power minus 1. The power of a lens of focal length of 1 meter is 1 diopter. Power of a lens is positive for a converging lens and negative for a diverging lens. Thus, when an optician prescribes a corrective lens of power plus 2.5 d, the required lens is a convex lens of focal length plus 40 cm. A lens of power of minus 4.0 d means a concave lens of focal length minus 25 cm. Combination of thin lenses in contact. Consider two lenses A and B of focal length f1 and f2 placed in contact with each other. Let the object be placed at a point O beyond the focus of the first lens A, figure 9.19. The first lens produces an image at I1. Since image I1 is real, it serves as a virtual object for the second lens B, producing the final image at I. It must, however, be borne in mind that formation of image by the first lens is presumed only to facilitate determination of the position of the final image. In fact, the direction of rays emerging from the first lens gets modified in accordance with the angle at which they strike the second lens. Since the lenses are thin, we assume the optical centers of the lenses to be coincident. Let this central point be denoted by P for the image formed by the first lens A, we get the equation 9.27. For the image formed by the second lens B, we get the equation 9.28. Adding equations 9.27 and 9.28, we get the equation 9.29. If the two-lens system is regarded as equivalent to a single lens of focal length f, we have the equation 9.30. The derivation is valid for any number of thin lenses in contact. If several thin lenses of focal length f1, f2, f3 are in contact, the effective focal length of their combination is given by the equation 9.31. In terms of power, EQ 9.31 can be written as P equals P1 plus P2 plus P3 plus 9.32, where P is the net power of the lens combination. Note that the sum in equation 9.32 is an algebraic sum of individual powers, so some of the terms on the right side may be positive for convex lenses and some negative for concave lenses. Combination of lenses helps to obtain diverging or converging lenses of desired magnification. It also enhances sharpness of the image. since the image formed by the first lens becomes the object for the second, EQ. 9.25 implies that the total magnification M of the combination is a product of magnification, M1, M2, M3, of individual lenses M equals M1, M2, M3. 9.33 Such a system of combination of lenses is commonly used in designing lenses for cameras, microscopes, telescopes and other optical instruments. Refraction through a prism. Figure 9.21 shows the passage of light through a triangular prism ABC. The angles of incidence and refraction at the first face AB are I and R1, while the angle of incidence from glass to air at the second face AC is R2 and the angle of refraction or emergence E. The angle between the emergent ray RS and the direction of the incident ray PQ is called the angle of deviation, delta. In the quadrilateral AQNR, two of the angles, at the vertices Q and R, are right angles. Therefore, the sum of the other angles of the quadrilateral is 180 degrees. Angle A plus angle QNR equals 180 degrees. From the triangle QNR, R1 plus R2 plus angle QNR equals 180 degrees. Comparing these two equations, we get R1 plus R2 equals A. The total deviation delta is the sum of deviations at the two faces, delta equals I, R1, plus E, R2, that is, delta equals I plus E, A. Thus, the angle of deviation depends on the angle of incidence. A plot between the angle of deviation and angle of incidence is shown in figure 9.22. You can see that, in general, any given value of delta except for I equals E, corresponds to two values I and hence of E. This, in fact, is expected from the symmetry of I and E in equation 9.35, that is, delta remains the same if I and E are interchanged. Physically, this is related to the fact that the path of ray in figure 9.21 can be traced back, resulting in the same angle of deviation. At the minimum deviation dm, the refracted ray inside the prism becomes parallel to its base. We have delta equals dm, I equals E, which implies R1 equals R2. Equation 9.34 gives 2R equals A or R equals A by 2. In the same way, EQ 9.35 gives dm equals 2I minus A or I equals A plus dm by 2. The refractive index of the prism is given by the equation 9.38. The angles A and dm can be measured experimentally. Equation 9.38 thus provides a method of determining refractive index of the material of the prism. For a small angle prism, i.e., a thin prism, dm is also very small, and we get n21 equals sin of A plus dm by 2 by sin A by 2 equals A plus dm by 2 by A by 2. dm equals n21 minus 1 into A. It implies that thin prisms do not deviate light much. Optical instruments. A number of optical devices and instruments have been designed utilizing reflecting and refracting properties of mirrors, lenses and prisms. Periscope, kaleidoscope, binoculars, telescopes, microscopes are some examples of optical devices and instruments that are in common use. Our eye is, of course, one of the most important optical device the nature has endowed us with. We have already studied about the human eye in class 10. We now go on to describe the principles of working of the microscope and the telescope. The microscope, a simple magnifier or microscope, is a converging lens of small focal length, figure 9.23. In order to use such a lens as a microscope, the lens is held near the object, one focal length away or less, and the eye is positioned close to the lens on the other side. The idea is to get an erect, magnified and virtual image of the object at a distance so that it can be viewed comfortably, i.e., at 25 centimeters or more. If the object is at a distance f, the image is at infinity. However, if the object is at a distance slightly less than the focal length of the lens, the image is virtual and closer than infinity. Although the closest comfortable distance for viewing the image is when it is at the near point, distance d is 25 centimeters, it causes some strain on the eye. Therefore, the image formed at infinity is often considered most suitable for viewing by the relaxed eye. We show both cases, the first in figure 9.23, A, and the second in figure 9.23, B, and C. The linear magnification m for the image formed at the near point D by a simple microscope can be obtained by using the relation given below. Now, according to our sign convention, v is negative and is equal in magnitude to d. Thus, the magnification is given by the equation 9.39. Since d is about 25 centimeters, to have a magnification of 6, one needs a convex lens of focal length, f equals 5 centimeters. Note that m equals h dash by h, where h is the size of the object and h the size of the image. This is also the ratio of the angle subtended by the image to that subtended by the object, if placed at d for comfortable viewing. Note that this is not the angle actually subtended by the object at the eye, which is h(u). What a single lens simple magnifier achieves is that it allows the object to be brought closer to the eye than d. We will now find the magnification when the image is at infinity. In this case we will have to obtain the angular magnification. Suppose the object has a height h. The maximum angle it can subtend, and be clearly visible, without a lens, is when it is at the near point, that is a distance d. The angle subtended is then given by tan theta naught equals h by d approximately equal to theta naught. We now find the angle subtended at the eye by the image when the object is at u. From the relations h dash by h equals m equals v by u. We have the angle subtended by the image tan theta I equals h dash by minus v equals h by minus v into v by u equals h by minus u, that is approximately equal to theta. The angle subtended by the object, when it is at u, equals minus f. Theta I equals h by f, as is clear from figure 9.23, c. The angular magnification is, therefore, given by the equation 9.42. This is 1 less than the magnification when the image is at the near point, eq. 9.39, but the viewing is more comfortable and the difference in magnification is usually small. In subsequent discussions of optical instruments, microscope and telescope, we shall assume the image to be at infinity. A simple microscope has a limited maximum magnification, less than or equal to 9, for realistic focal lengths. For much larger magnifications, one uses two lenses, one compounding the effect of the other. This is known as a compound microscope. A schematic diagram of a compound microscope is shown in figure 9.24. The lens nearest the object, called the objective, forms a real, inverted, magnified image of the object. This serves as the object for the second lens, the eyepiece, which functions essentially like a simple microscope or magnifier, produces the final image, which is enlarged and virtual. The first inverted image is thus near, at or within, the focal plane of the eyepiece, at a distance appropriate for final image formation at infinity, or a little closer for image formation at the near point. Clearly, the final image is inverted with respect to the original object. We now obtain the magnification due to a compound microscope. The ray diagram of figure 9.24 shows that the linear magnification due to the objective, namely h dash by h, equals m naught, which is given by the equation 9.43, where we have used the result as given below. Here h dash is the size of the first image, the object size being h and f naught being the focal length of the objective. The first image is formed near the focal point of the eyepiece. The distance L, i.e., the distance between the second focal point of the objective and the first focal point of the eyepiece, focal length phi, is called the tube length of the compound microscope. As the first inverted image is near the focal point of the eyepiece, we use the result from the discussion above for the simple microscope to obtain the angular magnification m due to it. Equation 9.39, when the final image is formed at the near point, is given by the equation 9.44. When the final image is formed at infinity, the angular magnification due to the eyepiece, equation 9.42, is given by the equation 9.44b. Thus, the total magnification, according to image is formed at infinity, is given by the equation 9.45. Clearly, to achieve a large magnification of a small object, hence the name microscope, the objective and eyepiece should have small focal lengths. In practice, it is difficult to make the focal length much smaller than 1 centimeter. Also, large lenses are required to make L large. For example, with an objective with FO equals 1.0 centimeters, and an eyepiece with focal length phi equals 2.0 centimeters, and a tube length of 20 centimeters, the magnification is about 250 as given below. Various other factors such as illumination of the object contribute to the quality and visibility of the image. In modern microscopes, multi-component lenses are used for both the objective and the eyepiece to improve image quality by minimizing various optical aberrations, defects, in lenses. Telescope. The telescope is used to provide angular magnification of distant objects, figure 9.25. It also has an objective and an eyepiece. But here, the objective has a large focal length and a much larger aperture than the eyepiece. Light from a distant object enters the objective and a real image is formed in the tube at its second focal point. The eyepiece magnifies this image, producing a final inverted image. The magnifying power m is the ratio of the angle beta subtended at the eye by the final image to the angle alpha which the object subtends at the lens or the eye. Hence m equals FO by Φ is given below.
Hi, I am Galileo. Do you want to know about the telescopes?
In this case, the length of the telescope tube is Φ plus Φ. Terrestrial telescopes have, in addition, a pair of inverting lenses to make the final image erect. Refracting telescopes can be used both for terrestrial and astronomical observations. For example, consider a telescope whose objective has a focal length of 100 centimeters and the eyepiece a focal length of 1 centimeter. The magnifying power of this telescope is m equals 100 by 1 equals 100. Let us consider a pair of stars of actual separation 1 minute of arc. The stars appear as though they are separated by an angle of 100 times 1 minute equals 100 minute equals 1.67 degrees. The main considerations with an astronomical telescope are its light gathering power and its resolution or resolving power. The former clearly depends on the area of the objective. With larger diameters, fainter objects can be observed. The resolving power, or the ability to observe two objects distinctly, which are in very nearly the same direction, also depends on the diameter of the objective. So, the desirable aim in optical telescopes is to make them with objective of large diameter. The largest lens objective in use has a diameter of 40 inch, approximately 1.02 meters. It is at the Yerkes Observatory in Wisconsin, USA. Such big lenses tend to be very heavy and therefore difficult to make and support by their edges. Further, it is rather difficult and expensive to make such large-sized lenses which form images that are free from any kind of chromatic aberration and distortions. For these reasons, modern telescopes use a concave mirror rather than a lens for the objective. Telescopes with mirror objectives are called reflecting telescopes. There is no chromatic aberration in a mirror. Mechanical support is much less of a problem since a mirror weighs much less than a lens of equivalent optical quality, and can be supported over its entire back surface, not just over its rim. One obvious problem with a reflecting telescope is that the objective mirror focuses light inside the telescope tube. One must have an eyepiece and the observer right there, obstructing some light, depending on the size of the observer cage. This is what is done in the very large 200-inch, approximately 5.08 meters, diameters, Mount Palomar Telescope, California. The viewer sits near the focal point of the mirror, in a small cage. Another solution to the problem is to deflect the light being focused by another mirror. One such arrangement using a convex secondary mirror to focus the incident light, which now passes through a hole in the objective primary mirror, is shown in figure 9.26. This is known as a Cassegrain telescope after its inventor. It has the advantages of a large focal length in a short telescope. The largest telescope in India is in Kavalur, Tamil Nadu. It is a 2.34 meters diameter reflecting telescope, Cassegrain. It was ground, polished, set up, and is being used by the Indian Institute of Astrophysics, Bangalore. The largest reflecting telescopes in the world are the pair of Keck telescopes in Hawaii, USA, with a reflector of 10 meters in diameter.